Okay, so till now we have discussed about processor allotment or process scheduling in uniprocessor systems, and we have just started our discussion of process scheduling in multiprocessor or distributed environment. Now, in that we have said that process scheduling in a distributed computing environment can be one of the two types. One is non-migratory, in which case we assume that when the process is created, at the time of creation of the process, you decide that on which of the processors the process is going to be executed. And once the process is given to a processor, it is fixed and it remains on that processor for its entire lifetime. In case of migratory scheduling, what can be done is, at some instant of time, you can assign the process to one of the processors, but in between you can decide that, okay, this is not the processor on which this job has to continue, but we'll rather migrate this job from this processor to another processor, aiming that such type of reassignment will improve the overall system performance. So accordingly, we can have either a non-migratory type of processor scheduling, or we can have a migratory type of processor scheduling. Okay. Now, obviously, whether we go for a non-migratory processor scheduling or a migratory processor scheduling, we have to have multiple number of tasks to be distributed among multiple number of processors. Okay. Now, these tasks can be created by a number of users where the tasks are independent, or it can also so happen that the same task can be broken into a number of subtasks. Okay, where we can find out whether these subtasks can be computed independently or not. That means for a particular job, for faster execution, we try to find out whether different subtasks of a given task can be concurrently executed. So for that, the concept that we have is what is called concurrent processing. Okay. So we'll come back to our scheduling in distributed environment sometimes later. Before starting the scheduling, let us try to find out what is concurrent processing, and when you break a task into a number of subtasks, what are the conditions that are to be followed, that must exist for the subtasks to be executed concurrently. Okay. So for that, let us take some statements. Say I have statements of the form, say A is equal to X plus Y, that is one statement. Similarly, I can have another statement, say B is equal to Z plus 1, maybe C is equal to A plus B, and we can have another statement of the form, say D equal to C minus 1. Okay. So I take these four statements, I call them as statement number 1, statement number 2, statement number 3, and statement number 4. Okay. And suppose these are the statements belonging to a particular task, and we have to find out how many of these statements can be executed concurrently. Okay. Now, if you study all these four statements, S1, S2, S3, and S4, you find that out of these statements, for statement number 1, which is a equal to x plus y, okay, this x plus y does not depend upon any previous statement. That means x and y are not generated by any previous statement. Okay. Similarly, when you come to statement number S2, which says b equal to z plus 1, okay, here again the variables which are used is z, and z is not computed in S1. That means for computation of statement number 2 or S2, we don't have to wait for the completion of statement number S1. Come to statement number S3, you find that it says C equal to A plus B. But A is computed in S1 and B is computed in S2. So naturally, S3 cannot be computed until and unless statement number 1 and statement number 2 they are complete. Okay. Come to statement number S4, which says D equal to C minus 1. Again, C is computed in S3, which makes use of two variables A and B. A is computed in S1, B is computed in S2. So naturally it says that statement number S4 cannot be computed before completion of S3 because value of C, which is used in S4, that is decided in statement S3. Okay. So S4 cannot be computed before S3, and S3 cannot be computed before S1 and S2. Whereas for computation of S1, I don't have to wait for any statement. For computation of S2, I don't have to wait for completion of any other statement. Okay. So this says that S1 and S2, these two statements can be executed concurrently. S3 cannot be computed concurrently with S1 and S2. Similarly, S4 cannot be computed concurrently with any of them. Okay. So that tells me an order in which these statements are to be computed. I can compute S1 anytime. So I represent this graphically where S1 is a node. I can compute S2 concurrently with S1. Okay. S1 and S2, these two can be executed concurrently. After completion of S1 and S2, then only I can compute S3. Okay. So I put it this way, S3, and S3 has to depend upon or has to wait for the completion of statements S1 and S2. So I put it in the form of a directed graph like this. Okay. Similarly, S4 has to be computed after S3 is complete. So I put S4 as another node in the graph, okay, and I have to have a directed edge from S3 to S4, indicating that S4 can be computed only after completion of S3, not before that. Okay. So I get a graphical representation which tells me the dependency among the different statements within a program segment like this. Okay. And such a type of graph is called a precedence graph. Because it tells us what is the precedence relationship among the different subtasks of a given task. Okay. So this precedence graph we have constructed with the help of this simple example. Now let us see a formal way in which we can study different subtasks of a given task, and we can find out the precedence relation among those subtasks. Okay. So to do that, we define two types of sets for a given statement or for a given subtask. Okay, subtask is nothing but a submodule of a given program. Okay, so we define two types of sets. One of the sets we will call as read set, and other set we will call as write set. Okay, so we define two sets, one is read set and other one is a write set. The read set of a given statement or of a given module is represented by RSI, where SI is the ith statement or ith module. Write set is similarly represented by WSI, where SI is the ith statement or the ith module. Okay. Now we define like this: the read set of a statement or of a module is the set of variables Okay. So you can define read set of a statement SI as it is the set of variables which are only referred in SI, but their values are not modified by SI. Okay. Similarly, we can also define the write set of SI as it is the set of variables Okay. So for the write set, it is the set of variables which are referred and modified by SI. Okay. So coming back to this example that you have taken for these four statements S1, S2, S3 and S4, you find that for statement S1, the set of variables X and Y, these are only referred. but their values are not modified by S1. Whereas the variable A, its value is modified by S1. Similarly, S2, Z is not modified by S2, whereas B is modified by S2. S3, it modifies C, but it does not modify A and B. Similarly, S4, it modifies D, but it does not modify C. Okay. So accordingly, we can have the read set and write sets of these variables as read set of S1 is X, Y, okay, whereas write set of S1 is the variable A, right? Read set of S2 is variable Z. Write set of S2, sorry, is the variable B. Read set of S3, A and B. Write set of S3 is the variable C. Read set of S4 is variable C, and write set of S4 is the variable D. Okay. So you can find out the read set and write set of every statement, and similarly for every module. Okay. If it is a program module, you have to find out that what are the variables which are only referred in that module, but their values are not modified, which becomes the read set of that module. Similarly, you have to identify the variables whose values may be referred as well as modified. Those will become the write set of that particular module. Now you can find out the precedence relation by studying this read set and write set. So in this example, we have said that we can execute S1 and S2 in parallel concurrently, but S3 cannot be executed concurrently neither with S1 nor with S2. Okay. So if you study the read set and write set, you will find out that two statements, say Si and Sj, I take any two statements, one is statement Si and another is statement Sj. Okay, I can find out what is the read set of Si, I can find out what is the read set of Sj, I can also find out what is the write set of Si, I can also find out what is the write set of Sj. Okay. So by studying this read set and write set, we can conclude that these two statements, Si and Sj, they can be executed concurrently, provided their write set of one does not intersect with any of the sets of the other one, and vice versa. Okay. So if write set of Sj does not intersect with write set of Si or read set of Si. Okay. Similarly, if the write set of Si does not intersect with read set or write set of Sj, read set and write set of Sj, then Si and Sj can be executed concurrently. Okay. So the condition of concurrency will be that read set of Si intersection with write set of Sj should be null. Okay. Similarly, write set of Si intersection with right set of Sj, that should also be null. Similarly, right set of Si intersection with read set of Sj, that should also be null. However, if the read sets intersect, that does not prevent the two statements from executing concurrently. Okay. So, read set of Si intersection with read set of Sj, that may be null or it may not be null. Okay. So, I must have the condition that read set of any statement should not intersect with the right set of other statement, and right set of any statement should not intersect with the right set of the other statement. However, if the read sets of the two statements they intersect, this does not prevent us from executing S1 and S2 concurrently. So, this will be the concurrency condition. Okay. And you will find that if two statements are concurrent, if they can be executed concurrently, then on a sequential machine, in whichever order you execute those two statements, your result after execution of the two statements will be same. That means if S1 and S2 can be executed concurrently, then on a sequential machine, if I execute S1 first followed by S2, or S2 first followed by S1, after completion of the two statements, I will get the same output. Okay. So, to break a task into a number of subtasks with the aim that I should be able to execute those subtasks concurrently as far as possible, okay, I must study the read set and write set of each of these subtasks to find out what will be the precedence relation among those subtasks. And once you find out the precedence relation, then only you can go for writing the code using any parallel language. Okay. Now let us take an example with a precedence graph and try to develop a code for that precedence graph to make use of the concurrency. Okay. So I'll take a precedence graph something like this. So this is the precedence relation. So this entire graph represents a complete task, whereas every node or every vertex in the graph represents a subtask of the complete task, okay, and the graphs represent the precedence relation among those subtasks. Okay. So here obviously it says that first you have to execute S1, After completion of S1, I can currently execute the subtasks S2 and S3. Okay. So S2 and S3 can be executed concurrently. After S2 is complete, the subtask S4 can be executed. And I don't have any precedence relation among S3 and S4. So S4 can execute concurrently with S3. Okay. After S4, I can have two more concurrent tasks. One is S5, other one is S6. Again, S5, S6 and S3, they can be executed concurrently. Okay. After completion of all these three, when S5, S6 and S3, all of them are complete, then only I can execute S7. Okay. So S7 cannot be executed concurrently with any of them. Okay. So that is what this precedence graph means. So naturally, when you build up such a precedence graph, you have to study the read set and write set of the given task. Okay. Now I didn't mention one thing, that in case the write set of one statement or one module intersects with write set or read set of some other module, then how to decide the order in which they have to be executed. This order is quite natural. It should come by the natural flow in the algorithm. That means when you develop an algorithm, whichever order you follow, that order has to be maintained for execution of those two statements. Okay. Now, given such a type of precedence graph, let us see how we can write a code for execution of this precedence graph, making use of concurrency as far as possible. Okay. So we have to write our code like this, that first we have said that first statement that has to be executed is statement S1. Okay. So I will put them under begin end construct. So let us use a Pascal-like language. So first we have to have a begin. Okay. Following begin, the first statement that has to be executed is statement number S1. Okay. After S1 is completed, I can create two processes. One process will execute S2 here. After completion of S1, I have to create two processes. One process will execute S2, the other process will execute S3. That means I have to have a system call for creation of a new process. Okay. So the system call that we will assume is a fork system call. So I have a system call called fork for creation of a process. Okay. And the fork system call has to work with a level. So I'll say fork a level L1. Okay. Now what does it mean? Whenever I say fork L1, then let me put it here. I create an additional process. One process will start execution from the statement at level L1, and the other process will continue with the statement following this fork statement. Okay. So after fork, since as per our precedence graph, we have to create two processes. One process will continue with statement S2, and the other process will continue with statement S3. Okay. So after execution of S1, I have given a fork statement which creates an additional process. So now I have two processes. One was the parent process, and other one is the child process that has been created. Okay. One of these two, either the parent or child, will continue with the statement at level L1, and the other one will continue execution with the statement following this fork statement. Okay. So now one of the process has to execute S2. So let us assume that this is the process which continues with execution of S2. Okay. And the other process has to continue with execution of statement S3. So I create two processes. One process executes S2, the other process executes S3. Right? After S2, the same process has to compute the statement number S4 because S4 comes in sequence after S2, and here I cannot have any concurrency as per our precedence relation. So after completion of S2, the same process will continue with the execution of S3. Sorry, S4. Okay. After S4, again I can have two processes. One process will execute S5, the other process will execute S6. Okay. So again, I have to make use of a fork statement with a level. So I'll put another fork statement, fork with level L2. So again, it creates two processes. One process starts execution at level L2. The other process continues with the statement following this fork statement. So I have level L2, and let me put the statement, say S6. It may be either S5 or S6, that does not matter. So let me put S6 here and S5 to be executed by the same process. So like this. Okay. So at this point, you find that I have three concurrent processes running parallelly. One is executing S5, the other one is executing S6, and the third one is executing S3. Okay. After completion of all these three statements, I have to execute statement number S7. But S7 has to be executed by a single process. I have three processes running concurrently. So the other two processes must be terminated when they have completed their job. So how do you do it? That is what is done by the join statement. Okay. So I have to put a statement join. Let us put that here. Right. So I have to put a join statement which has to work with an argument. I'll come to that later. After this join statement, the statement number S7, which is the last statement in this program module, has to execute, and then finally we'll have end of the program. Okay. Now, these being two independent processes, after completion of them, we have to indicate that after completion where they should go, what they should do. Okay. So after completion of S3, I should instruct that it should come to this join statement. Okay. So what I'll put is, I'll put go to statement or level, say L3, where L3 is the join statement. Statement that I have at L3 is join. Okay. Similarly, here this process also has to come to L3 after completion of statement S6. So I'll also put here go to level L3 to execute the join statement. Okay. Now you find that the process which is continuing with S5, that executes join statement after completion of S5. The process which is executing S3, that also executes join statement after completion of L3. The process which is executing S6, it also computes the join statement after completion of S6. Okay. For execution of S7, I need only one process. So I must have some provision so that the remaining two processes will be terminated. Okay. So how that is to be done? We have to use, along with this join statement, a argument. Okay. So let me put that argument as count. Okay. And I initialize the count with a value 3. Okay. How do you initialize the count? After studying your precedence graph, you find that at this point, all these 3 processes are to be combined to give you a single process. That means 2 processes have to be terminated and 1 process has to continue to execute this statement number S7. Okay. So that is why I have initialized the value of this variable count to 3, indicating that 3 processes are to be combined at a point. Okay. And the join statement has to work with this count argument.
So likewise, how many processes do you have to expect?
That depends upon your precedence graph. How many processes you want to execute concurrently?
There might be so many statements which have to be executed.
Yeah.
Then we are alerting S3 to L3. After completion of S3, we can alert the same process to S6 also.
Then you have to have the process communication mechanism. We'll come to that later. Okay. Here we are assuming that whenever required, we are creating the process. Okay. Once the process completes its task, it is either getting terminated or continuing with the rest of the task. Now, which one will be terminated and which one will continue, that is not sure. Okay. So any statement after completion of its task, it executes the join statement with argument count. Okay. Now, what is the purpose of this join statement? If we expand this join statement, the join statement performs this task. When I say join count, this performs the task like this. It decrements the value of variable count by 1. So count becomes count minus 1. Okay. After decrementing the count, if the process finds that count is non-zero, if count is not equal to 0, then quit or terminate. Okay. So if I expand this join count statement, the join count work like this. First, count is decremented by 1. After decrementing, you check the value of count. If count is not equal to 0, then the process is terminated. If the count is equal to 0, then the process continues. Okay. So here you find, since 3 processes will be executing this join statement, join count statement, and we have initialized the value of count to 3. Okay. So the first process which executes this join count statement, I still don't know that whether this process which is executing S5 will execute the join statement first, or the process executing S3 will execute join statement first, or the process executing S6 will execute join statement first. That depends upon what is the complexity of these statements, how much time this statement will do. And here this statement does not necessarily mean that it is a single statement, it can be a module. Okay. So whichever process executes this join count statement first, count will be decremented by 1. Okay. So the first process to execute join count statement will see that value of count is equal to 2 after decrementing, which is non-zero. That means that particular process will be terminated. Okay. Second process which executes join count statement, that will again decrement count by 1. So earlier value of count was 2, it will decrement the value of count by 1, so that becomes now equal to 1, which is again non-zero. So the second process will also be terminated. Okay. The third process to execute this join count statement, it will again decrement the value of count by 1. So earlier the value of count was equal to 1. After decrementing, the value of count becomes equal to 0. Okay. So the third process finds that count is equal to 0. Because count equal to 0, so third process will not quit, or the third process will not be terminated. So it is the third process which will execute statement S7 and finally come to the end of the program.
The first process is S5, which has executed join statement.
Yeah, that will be
and
terminated.
it is quitted. Means it is terminated.
Yeah.
Then what about the variable values in the memory? Are they kept like that?
Yeah, they will be kept. All the image.
The process is terminated by the
The first process is terminated, but the program is not terminated. Program is still continuing. Okay. So the entire memory map of the process will be kept.
Here count is the global variable. Global variable.
Count is
Global variable.
global to this particular process or this particular task. Okay. So this is a very, very simple precedence graph that we have taken for writing such a particular concurrent program. Okay. And in this precedence graph, we have seen that the processes are joined only at one point. I can have a complicated situation where the processes can be combined at multiple points, not only at one point. Okay. So when the processes are to be joined at multiple points, in that case, it may so happen that defining a single count variable is not sufficient. I can go for multiple count variables. Say for example, count 1, count 2, count 3, and so on. Okay. So let me quickly take another simple flow chart, simple precedence graph, and see how we can write a forked join based structure for that. So I take a very simple precedence graph like this, say S1, S2, okay, S3, S4, S5, S6, then S7. So this is the precedence graph that we have. Okay. How we can write? So you find that there are 2 points where the processes are to be joined. Here 2 processes are to be joined. Here also 2 processes are to be joined. Okay. So I can write a very simple fork join structure for this. I start with again begin, then S1, then fork L1. Okay. At L1, I have statement S3. Okay, then I have S2, then I have fork L2. Okay, so at L2 I'll have statement say S5. Here I have S4. Now after completion of S4 and S5, two processes are to be joined. So I'll have level say L3. At L3 I put say join count 1. Okay, and after S5 I put go to L3. Okay, so after completion of S5, the process comes here, it executes join count 1. After S4, this process comes here, executes join count 1. One of these two will be terminated, and the one which survives, that will continue and execute S6. After completion of S6, I have to combine two processes, one executing S3 and the one executing S6. So I'll put a level L4 with join count 2. Okay, and here I'll give go to L4. Okay, then the final one will continue S7, and then you come to the end of the program. So you find that I have to have two count variables, one is count 1 and count 2. This join statement combines two processes. This join statement also combines those two processes. That means both count 1 and count 2, they have to be initialized to value 2. Okay, so here I have to have count 1 equal to 2, count 2 also equal to 2. Okay, so this initialization has to be done here. Okay, so now you see that given any task, you can break the task into a number of subtasks. By studying the subtasks, you can find out the precedence relationship, or you can determine the precedence graph of that given task. And once you have the precedence graph, you can write a concurrent program for to translate that precedence graph into a code. Okay. So with this, we stop here today. Next day, we'll continue with this topic for some more time.